Chapter 3 is all about water. Water is the molecule of life. And part of the reason that it's so important for biology is its chemical properties. So if we think about a water molecule, what it is one oxygen atom joined to two hydrogen atoms by polar covalent bonds. What that means is that the oxygen is highly electronegative. It loves electrons and pulls them towards itself. So the consequence of this is that one side of the oxygen molecule is partially negative, and the other side of the water molecule, on the hydrogen side, is partially positive. You can also have non-polar covalent bonds, where two atoms share electrons equally. So for example, if we had two hydrogen atoms sharing a pair of electrons, they're equally electronegative. And so neither side or the other is going to be more positive or more negative than the other. So when molecules are polar, they react differently with water. Molecules that are polar mix well with water. Now water is polar, water mixes with water, but other polar molecules that have either partially or fully charged sides are going to be attracted to water. Molecules that, and that's called hydrophilic. Molecules that are mostly made of non-polar covalent bonds that share electrons equally are not going to have an attraction or a repulsion to water. They're not going to mix with water. So we call these hydrophobic molecules. So non-polar molecules are hydrophobic. And then of course there are some molecules that are both hydrophobic and hydrophilic. So here we have a phospholipid which makes up our cell membranes. The top half, called the head group, is polar. It's got charged groups in it. It's got a positively charged nitrogen, and this phosphate group's going to ionize in water and be negative. But these tails that are just made of carbons and hydrogens attached to each other are made of non-polar covalent bonds. And so this molecule is amphipathic. Because water is a polar molecule and because it has positive sides and negative sides, these opposite partial charges can be attracted to one another. So the positive charge on one side of a water molecule can be attracted to that opposite negative charge on a different water molecule. And this attraction between opposite partial charges is called a hydrogen bond. I said this in the last video. I want you to write it down. Make sure you have it in your notes. One water molecule is made of polar covalent bonds. H2O is made of polar covalent bonds. Hydrogens hooked to oxygen are hooked together through polar covalent bonds. But different water molecules are attracted to one another through hydrogen bonds. Hydrogen bonds are the attraction of opposite partial charges. Hydrogen bonds occur between polar molecules. And it's these properties, the fact that water is polar and that it can hydrogen bond with other polar molecules, that gives it so many characteristics that make it essential for life. So some of those characteristics that water has is cohesion. Water molecules stick to each other. It's good at moderating temperature. It helps ice float, and it's an excellent solvent. And all of these are really important for biology. So let's start with cohesion. Cohesion is the property of molecules of the same kind sticking together. So that's what happens in a glass of water. These opposite partial charges attract one another, and hydrogen bonds hold the water together. And so this is the property that allows water striders to walk on the surface of the water, because the force of the bug pushing down is less than the force of all the hydrogen bonds holding the water molecules together. This is also why you can kind of overfill a glass of water. That little bubble of water on top is caused by cohesion or surface tension, where the water molecules stick together. Not only can water molecules stick to each other, but they can also stick to molecules of different types. Adhesion is when molecules of different types stick together. And this is actually the property that allows water to move up through plants. So trees don't have a heart, right? But they still have to transport fluid, 60 feet in the air if it's a big tree. The way that this happens is that water evaporating out of the top leaves the plant, and then water molecules roll up the vessels of the plant through cohesion and adhesion together. When you go to the doctor's office and they do a finger prick and the blood gets sucked up into that little glass tube, well, it's not really getting sucked. It's just the water in your blood sticking to the sides of the tube, sticking to each other, and rolling up the sides of the tube. Another important property of water is its ability to moderate temperature. So it takes an incredible amount of energy to raise the temperature of water. In other words, water has a high specific heat. And when you do reach that temperature that allows it to break the hydrogen bonds and evaporate, it cools the area it leaves behind. So hydrogen bonds are really, really wimpy, but in a glass of water, each water molecule is connected to 4 other water molecules through hydrogen bonds. And so it takes a lot of energy to break all of the hydrogen bonds in a glass of water to get it to evaporate or boil. When we think about what happens to water when it freezes, in a liquid glass of water, some of the water molecules are 1 hydrogen bond length apart, but others are actually closer to each other. These hydrogen bonds are constantly being formed and broken and reformed, and so the water molecules are actually closer together. But when you freeze the water molecules and they slow down, each water molecule connects to the next one in a crystalline pattern, and they actually spread out and take up more space. That makes frozen water less dense than liquid water, and ice floats. And that's important for Arctic ecosystems, but also ecosystems in the Midwest. When a pond freezes, it freezes from the top down. And that's good, because if it froze from the bottom up, all the frogs and the fish that were in the water would get frozen solid every time the temperature drops below 0. Another important property of water is that it is a good solvent. A solvent is a dissolving agent, and in biology, the solvent is usually water. Water makes an excellent solvent because it's polar, because it has one side that's partially positive and one side that's partially negative. So some vocab words here. Water is the solvent. The solvent is the dissolving agent. The stuff that gets dissolved is called the solute. And the mixture of the two makes up a solution. So if we make a saltwater solution, the positive sides of water surround the negative ions, and the negative sides of water surround the positive ions. This wrapping around these ions is called solvating it. It's making it into a solution with the solvent. And water can do that because it's polar. A glass of pure water, it's not actually all H2O. The water molecules are constantly breaking apart and reforming. So water splits up into a hydrogen ion, meaning a proton without an electron, and a hydroxide ion, an OH minus. So it's got that extra electron from the hydrogen. Although it's probably more accurate to say that really we get H3O plus, hydronium ion, and that hydroxide ion. So in a glass of pure water, this forming and reforming and breaking apart of water is constantly happening. And when that happens, the concentration of hydrogen ions and the concentration of hydroxide ions is equal to each other. And it's about 1 × 10⁻⁷ moles per liter. An acid or a base is anything that shifts away from that equilibrium point where there's an equal concentration of hydrogen ions and hydroxide ions. If you have a higher concentration of hydrogen ions, you have an acid. And if you have a higher concentration of hydroxide ions, you have a base. I really like this picture that your textbook has showing the difference between an acid or a base with this little beaker here. So pure water has an equal concentration of hydroxide ions and hydrogen ions. An acid has more hydrogen ions, and a base has more hydroxide ions. So you can see some examples of some typical acids and bases here. So when we talk about the pH scale is a more convenient way of thinking about the concentration of hydrogen ions in the solution. In a glass of pure water, the hydrogen ion concentration equals the hydroxide ion concentration. And when you multiply those two concentrations together, what it gives you is the equilibrium constant for water, which is a constant. It doesn't change. It's 10⁻⁴. But that's a really inconvenient number. It's 0.0000000000000001. So instead of using these really tiny decimals to express the hydrogen ion concentration or the hydroxide ion concentration for water, we use the pH scale. What the pH scale does is takes the negative logarithm of the hydrogen ion concentration. So it sounds kind of complicated, but when you punch that into your calculator, what it means is, for example, if we have pure water, the hydrogen ion concentration equals 1 times 10 to the negative 7th. Well, when you put 1 times 10 to the negative 7th negative logarithm into your calculator, what it's going to tell you is that equals 7. And so pH 7 is when the hydrogen ion concentration and the hydroxide ion concentration equal one another, which is the value 1 times 10 to the negative 7. When you have a glass of pure water, the hydrogen ion concentration equals the hydroxide ion concentration. But if we shift the hydrogen ion concentration, the hydroxide ion concentration is going to shift in the opposite direction, but the equilibrium constant for water is going to remain constant. So for example, if we make something that has a pH of 6, the hydrogen ion concentration is 10 to the negative 6. But we can figure out what the hydroxide ion concentration is because the equilibrium constant for water is a constant. So if the hydrogen ion concentration went to 10 to the negative 6, then that means the hydroxide ion concentration is now 10 to the negative 8. Just a friendly reminder about multiplying numbers with exponents. When you multiply these numbers that have the same base but different exponents, the exponents add together. So that's how I got 8 from these two. So because of that, if you're given a problem that tells you the hydrogen ion concentration, you can figure out the pH, or you could figure out the hydroxide ion concentration, or vice versa. If I told you the hydroxide ion concentration was 10 to the negative 2, I could ask you, what is the pH of this solution? And the way to figure that out would be to first figure out the hydrogen ion concentration, which has to be 10 to the negative 12, because when we multiply our exponents, it equals 10 to the negative 14. And so if our hydrogen ion concentration is 10 to the negative 12, that means our pH is 12. Two more examples of the type of problems you should expect to see on the Unit 1 exam. So again, if we start with the problem where it tells you the pH is 3, and the question asks you, what is, let's see, how did I write this question? What is the hydroxide ion concentration? That's a question. Okay. The way to solve this problem is to recognize that pH 3 is the same as saying that the hydrogen ion concentration equals 10 to the negative 3rd. If our hydrogen ion concentration is 10 to the negative 3rd, then our hydroxide ion concentration has to be 10 to the negative 11th. I could also ask you a question where I tell you that the hydroxide ion concentration is 10 to the negative 8 and ask you what is the pH. So again, to get to this, we have to think, what is the hydrogen ion concentration? If our hydroxide ion concentration is 10 to the negative 8, then our hydrogen ion concentration has to be 10 to the negative 6, which means that our pH is 6. One more thing to think about with these problems, the pH scale is a logarithmic scale, which means each step is not a one-fold change, it's a 10 times change. If we're moving from pH 4 to pH 7, concentration is not changing 3 times, but 10 to the 3rd or 1,000 times more. Okay? So, and also remember, as we go from pH 4 to pH 7, from 4 to 7 means we're getting less acidic or more basic. So the hydroxide ion concentration is actually going up and the hydrogen ion concentration is going down. So we would have 1,000 times more hydroxide ions and 1,000 times fewer hydrogen ions. Small change in the value of our pH is actually a dramatic change in the concentration of hydrogen ions. And so living systems use buffer systems to either absorb excess hydrogen ions or release hydrogen ions to keep the pH constant for the inside of organisms.